This is my 8-bit computer as it stands so far. It has a handful of components fleshed out so far. We have the clock up here. We have two registers, my A register and my B register, as well as the arithmetic logic unit, my ALU. So this will just take whatever in the A and B registers and either add or subtract them. We have over here the bus that's used for either outputting the values from any of these three components or for inputting the values to the A or B register. We can go ahead and start adding values into the A register. As soon as we do, you will see the values in the adder reflect whatever's A plus B. B is currently 0, so essentially the adder will just show whatever's in A as well. Currently I have it set up to, it looks like 42. So if I read that value from the bus, we take 42 and we add nothing, and we correctly have 42 in the output. If we just change any of the bits, you can see that they get correctly reflected on the adder. We can stop reading from the into the A register. We can make sure that our subtraction is set to be low, so we're actually adding the values. In the A example, it was fine just because it's B subtracted from A, so it's really 0 minus whatever's in A has the same value as A. Let's go ahead and clear the A register so we can do the same sample with B, where we now just take whatever in the bus, put it into B, and see that B plus A of 0 equals whatever in B. And again, we can just change the values to whatever we like, and it correctly shows up in the adder. Now actually looking at the numbers, this is 7, so 7 plus 0 is 7. We can stop reading on B, start reading again onto A, so it would be 7 plus 7, so we expect to see 15 in here, which I believe is 1110, no, 1100, so it's going to be, let's just see what it is. Yeah, so 110, so 7 plus 7 is 14, 8 plus 4 plus 2 equals 14. I think I said earlier that 7 plus 7 is supposed to be 15. Clearly that's wrong. So great, we can do simple addition of 7 plus 7. Can we do anything else? Let's try 7 plus 42. Try to get some of these other higher order bits involved to make sure that, that those will work as well. So 42 is represented by 0, 0, 1, so 0, 0, 1, 0, 1, 0, 1, 0. Alright, so to convert from binary, this is the 1-bit, the 2-bit, the 4-bit, the 8-bit, the 16-bit, the 32. So it's 32 plus 16. 32 plus 8 is 40, plus 2 is 42, great. 42 plus 7 is 9, so we expect this to be, 42 plus 7 is 49, so we expect this to be 49. So this is 32 plus 16, it's 48, plus 1, 49, great. So far this tracks. Now we can look at how subtraction would work. So this is still 42, subtracting 7, that's going to wind up being 35. So we will take the subtraction signal and take it high, and then see that 32 plus 2 plus 1 is 35, so we get the expected result. The ALU is essentially built with a transceiver, an 8-bit transceiver that just basically is used to enable and disable the output from the ALU to the bus. Currently the ALU is not hooked up to the bus. It's not needed for this example, so I didn't bother with that. And then we string two adders together. The adders are 4 bits each, so 2 adders gets you 8 bits. The adder on my right side here is the 4 low order bits, so these bits, and the adder on the right side is the higher order bits, so the first 4 bits. The way that they actually string together nicely is that the carry out, so the one that you may carry over when you're doing addition, for the last digit, the highest order digit, there's a carry out signal here that then goes into the carry in signal here. So that extra 1 gets to get added from the highest order bit to the lowest order bit here. And then we have the A register that's essentially plugged directly into the 8 A inputs of these 2 chips. The B register is a little more complicated in that we want to be able to support subtraction. The adders by their names don't support subtraction, but the simplest way to do that would be to convert whatever value is in here into a negative number and just add that negative to what's ever in here. Negatives in binary are represented using something called choose complement, which basically just means that we invert all the values and add 1. So this is the positive 7, and to get negative 7, it would be 1, 1, 1, 1, 1, 0, 0, 1. Right? So just flipping these bits, and then taking the result of that and adding 1. The way we invert those bits is by piping them into these 2 XORs. Again, this XOR is used for the high order 4 bits. This XOR is used for the low order 4 bits. When the signal is low, we are essentially XORing each one of these bits with 0. So that just winds up being whatever the input bit is. So 0 XORed with 0 is 0. 0 XORed with 1 is 1. So there's no change. But when we set the XOR signal to high, 1 XORed with 0 is 1. 1 XORed with 1 is 0. So it just flips the bits very nicely. As I said, choose complement is achieved by flipping the bits and adding 1. How do we add the 1? Well, we just use the carry in value on the lower order adder to add 1. That input's not being used for anything else, and if we just tie it to this signal, it will be high, i.e. 1, whenever we need it to be for subtraction. So that essentially achieves a negation of B. Now, can we verify that that's what's happening here? Sure. So I'm going to take the A register and stop reading it from the bus, and then I'm just going to clear it out. So it's going to be 0, minus 7. It's going to show you the value of negative 7 there. So according to what I said, we expect the first, 5 bits to be 1, 2 bits to be 0, and then 1 bit to be 1 again. So if we just clear out the A registers by hitting the clear line, we see that exact output. So this is the ALU with the 2 registers inputting data and communicating data between A and B through the bus.